Right. So we have two speakers, Sriram Ramaswamy and Prashant Singh. And Sriram is first. Yeah, go ahead once you find it.
That's it? Wow. Yeah, it works. Can I start? Oh, yes,
start.
Yeah. Okay. I'm sorry for the sort of ridiculous title. I think one day I got a message saying you haven't sent your title in abstract, and I sort of came up with a kind of silly title. But it's a accurately descriptive title. It's just not very witty. So first, thank you very much for the invitation to speak. Second, congratulations RRI on hitting the age of 75. I think I gave my first talk in RRI was in this room, and it was probably about half of that 75 years ago, about 37 years ago. And yeah, so it's great. I love talking in this room. Okay, so my talk will consist of an introduction to non-reciprocal interactions, and then a study of the work is motivated by active matter considerations, but the models aren't overtly active matter. There are two kinds of models of continuous spin magnets in a certain sense, with two different kinds of non-reciprocal interactions with different consequences. And I'll tell you a bit about each. Okay, now it's clear that interactions, in the social world or in the living world are in general pretty non-reciprocal, and as many of us will have experienced in the course of our lives. There are some particularly dramatic examples like predator-prey problems, or apparently locusts. Apparently the reason that locusts flock, or the origin of the aligning interaction of locust orientations and velocities, is because one is trying to eat the other and the other is trying to run away, which does in fact lead to a ferromagnetic alignment of their orientations and velocity vectors. More generally, when you have sensing, signaling, ligand receptor binding and so forth, even though one part of that interaction is something binding to something by a pair potential, because there's a whole information cascade that takes place after that, what the ligand does to the receptor and the receptor does to the ligand are very different, and in that sense, those interactions are non-reciprocal. It will not surprise you to know that being at thermal equilibrium rules out non-reciprocal interactions. So today I'll tell you about a couple of different kinds, as I mentioned. The subject, actually in some sense, people have discussed non-reciprocal interactions in different forms, including predator-prey and so forth, for a very long time. But the subject is certainly enjoying a huge revival and a huge amount of development, especially in the context of models of active matter. But as you'll see, actually, we started playing with non-reciprocal magnetic models about the same time as we started playing with self-propelled particles and active systems and so forth. And I'll tell you a little bit about that work. Before I go further, I'll just show you one real-life, purely mechanical example, just for fun, of non-reciprocal interactions. So if you have a surface which you vibrate up and down, and you place an object on it. So the idea is you have an object like this. This is the top view of something that you're shaking up and down. This is a medium around this object. And if this object is pointing in a direction n and has a position r, and the medium is an elastic medium described by a displacement field u and, let us say, some kind of Lamé elasticity, and the object moves through the medium, then it turns out that two such objects have an interaction which is quite non-reciprocal. So one such object will move like this, if the movie obliges me, of course, yeah. So one of these guys will move like this by transducing the vertical shaking energy into horizontal motion. And if you have two such objects, what happens really is that each such object distorts the medium around it in a certain way, and another similar object placed in that medium senses that distortion. The fact that each of these guys is moving in a direction primarily set by which way it is pointing, and the fact that the interaction has not to do with directly moving their centers of mass towards or away from each other, but in reorienting, a typical taxis kind of interaction, makes the interaction between such particles non-reciprocal for a very simple reason. It turns out if you do the maths, you find that if you have a particle ahead and a particle behind, the distortion produced by the particle in front is sensed by the particle at the back, and the one at the back is moving this way, and it turns out the distortion it produces is strongly screened. So these two guys talk to each other in a way that's very non-reciprocal. This guy doesn't sense this guy coming, this guy senses the presence of that guy, and as a result you get this kind of nice pursuit and capture behavior. So this is purely the recreational, frivolous part of the talk, just to show you these kinds of things really happen, and you don't have to have living stuff. A very rudimentary realization of self-propulsion and this kind of tactic interaction is enough to produce non-reciprocal interactions. Now, my talk is not about this. This was just kind of an appetizer. Yes? I mean, it depends on what, each one, it's a layer of particles. These are millimeter-sized beads, and we are shaking everything up and down. In principle, none of this stuff is passive because all of it is constantly dissipating energy. But if somebody gives you a general bath of some sort and doesn't tell you what it is, if you want to detect whether that bath is a thermal or a non-thermal bath, you need the right kind of tools. So if you're a round particle, you probably don't have what it takes to discover that that medium is non-thermal. Yeah. Yeah. Here the beads are very important. Here the interaction is entirely through the medium. You need something. You need you need an intermediary. In some sense, look, for instance, even hydrodynamic interactions are non-reciprocal in the sense that if something produces a flow and something reorients. But if you're very pedantic about what you mean by non-reciprocal, maybe what you can say is that even at thermal equilibrium, transiently the interaction between two objects which are moving each other because of flows they create is anyway non-reciprocal. But if you want interactions that are non-reciprocal sort of at zero frequency, or not as zero, if you want an effective instantaneous non-reciprocal interaction, you do need to be out of equilibrium. So I think
the beads can be passive, right? There's no need for the beads.
The beads don't need to, but in this particular experimental system, I'm saying everything is being shaken by the same vibration. You could imagine a thermal bath, and
in a simulation, say you could imagine that the beads are not being shaken.
Sure. They're just actually, you could endow them with just plain Brownian motion.
But it would
Absolutely, sure, yeah, sure, absolutely. Because in fact, the analysis that we do is to treat the beads as something governed by Lamé elasticity, but the bead medium is being forced actively. So the beads are passive except for where they're being forced by the active particles. So in that sense, yeah. But again, you could ask, if one wants to be very precise and very pedantic about what one means by reciprocal or non-reciprocal interactions, clearly if you have two objects interacting via a pair potential, then the force on A due to B is minus the force on B due to A. But if you have two objects in an ambient medium interacting in some way, then in principle that momentum balance doesn't have to be, yeah?
But that's even true for charged particles in a magnetic field. They don't satisfy Newton's law.
Sure. So I mean, the particular kind of broken time reversal invariance that you have for particles in a magnetic field, I mean, you know, the trouble is that to some extent it becomes a question of a name. It's not a, you're not continuous. You can break time reversal dissipatively or non-dissipatively. If you break time reversal dissipatively, then I'll call that this kind of activeness. But merely having a magnetic field indeed makes time reversal implemented differently, and one has to keep that in mind. But here, actually, you can certainly write down models of this sort in which the position coordinates of systems do to each other what the velocities do for charged particles in magnetic field. So you can cook up examples like that, which was in somebody's talk yesterday, day before. Yeah. So, you know, odd elasticity is an example where the displacements of particles do what otherwise the two components of the velocity would do for charges in the magnetic field. Anyway, just to remind people of what you all know, imagine you have some, just to make it very clear that regardless of whether the dynamics is taking place in an ambient medium, regardless of the dynamics at the level of the particles in question is itself momentum conserving or has a medium, really you can ask about the effective interactions. You've got a bunch of particles, you've got some system with microstates or coordinates or anything labeled by A, B, etc., and some kind of master equation. Then you all know that a steady state of this sort is possible only if the transition probabilities obey this relation for any string of microstates. And you know that if they do obey that, you can construct the steady state by arbitrarily calling the weight of one configuration some p, and then successively determining all the others via the ratios of the transition probabilities. And you know that this lovely condition will guarantee that you can do this consistently. It's sort of a curl-free condition. And you can view the configurational energy of the degrees of freedom that you're looking at as emerging from this analysis. You can say that, look, I don't know about the microscopic Hamiltonian of this system. I have these W's, and it's interesting that the ratio of WAB to WBA is determined by the difference of a property purely residing in B to that property purely residing in A. And that's the object we'll mean by the energy. And so in some effective sense, velocity is downhill along gradients of that velocity. So if you apply this to a collection of particles moving around, then in a translation invariant system, then the fact that the interaction depends on, say, the differences of positions guarantees that the effective force on the degrees of freedom you're monitoring will be reciprocal. And so you can stop worrying about non-reciprocal interactions in a thermal equilibrium system. And clearly, therefore, if you break detail balance, that opens up the possibility of non-reciprocal dynamics in general. So if you've got a collection of particles and you just say it's in contact with some kind of bath, I'll describe that bath by some kind of noise, and then if I write the equations of motion in a force balance sense, and I know the forces, the velocity dependent, the velocity independent parts of the forces, then it opens up the possibility at least of non-reciprocal interactions. It's not demonstrating that it's there, just saying that you can have a dynamics of this sort. And clearly this kind of dynamics is going to be important if you want to send information in a directed way, in signaling and so forth. So this is why we're interested in it. So for reasons that I don't particularly remember now, more than 20 years ago, we started worrying about magnets with non-reciprocal interactions. Okay, and with motivations that I think were not even as sophisticated as this, we were just curious to know. I'll come to that in a second. I'll tell you a little bit about this old work and what we did with it recently. So what I'm going to tell you about today is two problems. This one I'll tell you about later. Don't worry, I'm not going to narrate only the story of what we did in 2002. I'm actually going to tell you about something that's ongoing, motivated by that. But before I do that, I'm going to talk about another kind of non-reciprocal magnet. And this started out in the PhD work of these people and is currently the work of Pankaj Popli, a postdoc, and very much involves Ananyo Maitro. Excuse me. Yeah, this problem is actually motivated by flocking models. You all know flocking models. They were invented by Reynolds or by somebody else, and therefore they're called the V-check model. And you know the idea that you have these creatures, they have a heading, they're going in a certain direction, they try not to bump into each other, they try to kind of stay with each other, but most important from the point of view of the present discussion, they try to align their velocities with each other. And you know that what happens as a result of this is that at high density and at low noise, you get an ordered state, right? And you also know that you can take this model and either actually by derivation or by pure unaided reason alone, write down the continuum field theory corresponding to it, replacing the orientations of the individual particles by a vector field P, replacing the number density, denoting the number density of those particles by a concentration C, writing down on general symmetry grounds an equation of motion in which you have something that tends to form a local moment. That local moment is not just an orientation but a velocity. It carries the concentration, it tries to line up with its neighboring moments, and it carries spatial variations in itself as well. And there's noise, and maybe it likes to align with respect to gradients of the concentration. This is the Toner 2 field theory corresponding to the V-check model. And among the reasons why this model is so celebrated is that these guys showed by a calculation that is qualitatively right but still quantitatively wrong, that these nonlinearities, and this in particular, even in the presence of noise, allow a state in 2 dimensions with long-ranged orientational order. So seemingly, obviously it doesn't break Hornberg, Mermin, Wagner, because that was a theorem built for thermal equilibrium systems. But what's interesting is the way in which it gets around it. And the way it gets around it is that the nonlinearities singularly renormalize the stiffness. And as a result, the arguments that would have given you quasi-long-range order in 2 dimensions now give you long-range order in the low temperature phase, low noise phase. Okay? Now, the reason I'm mentioning this is that the sort of physical understanding of this anomalous stiffness had to do with the idea that these are flying XY spins. So these are orientations that actually tell you about movement. So these are little arrows carried by particles that move around, and they move around with a velocity determined by which way they're pointing. Okay? So the question is that essential, or is there a way of building a fixed XY spin lattice, so a fixed lattice of planar rotors with a local interaction, deviating minimally from ordinary XY, incorporating some non-equilibrium element that doesn't break rotation, such that the model is still O2 invariant, but can condense into a state with long-range XY order? So that was the question. The answer is yes. But let me just tell you the story. Okay, so we consider XY rotors on a lattice. For completeness, because of our interest at that stage, this is Lokershi's PhD work partly, we wrote down a dynamics of an orientation and a conjugate classical spin angular momentum of these objects about their center of mass, if you like. So the dynamics is going to be that if there's a local angular momentum S, it turns P, and if the P's of neighboring sites aren't aligned, then there's an aligning torque acting on S. In addition, because this is a system in contact with some kind of medium, S actually has a damping. So you can see from this immediately that unless you do something weird and make the damping negative, S will be a fast variable, you can get rid of it, and you can write in effective dynamics in terms of P alone. But there might be physical regimes of interest where the rotational inertia is important. We'll talk about that. The important aspect of this model from our point of view is that we allow the interaction, the exchange coupling, if you want to call it that, between the P's to be sensitive to the fact that these guys are actually pointing in some direction in space. So imagine that this is one rotor and this is another rotor drawn suggestively as birds with a vision cone. So we allow for the possibility that this Jij is not symmetric, and the idea basically is that if I is in front of J or I is behind J, front of and behind defined with respect to pi, right? Then the interaction cares about that. Now, it should be immediately obvious that this torque cannot then be derived from a potential energy like Jij pi dot pj, because by construction Jij times pi dot pj can only pull out the symmetric part of Jij, right? So this is the idea. Yes? This is just classical mechanics with damping. This is just theta dot is omega, and this is I omega dot is del squared theta is finally all it will be, right?
So
P is cos theta sine theta.
That's the orientation, yeah.
S is the spin angular momentum conjugate to theta. I'm just writing it in an overly general way. I should have written it as theta dot is omega. So each S is this. So here's the rotor. This direction is P, and the angular momentum. This guy's moment of inertia times its angular velocity is S.
Okay.
It's literally, this is just the trivial Hamilton equation, and this is the equation for the angular coordinate being turned by the angular momentum.
So the torque, that's the...
No, this is the torque. Torque comes into an equation for the momentum. It can't come into an equation for the orientation.
Okay. Oh, so that's the torque. The
Aligning torque.
Okay, and this is...
S is the spin angular momentum of this object about its center of mass, if you like.
Okay.
I mean, you can think about it in different ways. You can ask, is that really a physical moment of inertia, or can it be behavioral, etc. You can ask whether, for a collection of living, breathing, or signaling objects, whether their sensing and rotating is because of a mechanical torque or something else, or because of an internal decision-making program, right? But what I'm just saying is that in a sense, this is overkill, but I wanted to write this in generality for some reasons that will become clear later. So I have an angle and an angular momentum corresponding to the angle. And this, sorry? Yeah, it's all in the plane. There's just, you can do it in more dimensions. As I said, this is overkill. Yeah. That's all it is, just mechanics. And I've also introduced a damping on the angular momentum. And the damping is always proportional to a damping coefficient times a velocity. So it's a momentum divided by an inertia, always. I'm just being pedantic because I want to keep track of this inertia parameter. So it's a very conventional pair of equations of motion. The non-conventionalness only comes into Jij. Okay. And so the idea basically is supposing the interaction cares about which way, so let us say here is site I and there are the neighbors. So here is site I, here is site J. If the interaction cares about the angle between which way I is pointing and the vector from I to J, so if I have a neighbor there and I'm pointing towards it or I'm pointing away from it, I interact differently. So my interaction with it depends on which way I am pointing. Its interaction with me depends on which way it is pointing. Which is entirely reasonable if you think of vision-based interactions, but it won't flow from an energy function. You're still not satisfied. So I can take, yeah, tell me. Huh? You sure? Okay, all right. So then I'll write down the interaction coefficient Jij as some background J plus a piece that cares about which way P is oriented with respect to the vector from I to J. Right? And as a result, depending on whether P dot Rij is say +1 or -1, just for simplicity, you can get an interaction which is J minus A or J plus A. So what can happen, therefore, is if I've got this guy and this guy, for this guy, the interaction strength is going to be the inner product between that guy and the vector from it to this guy. For this guy, the interaction will be J plus this dot that. So this, roughly speaking, this will have an interaction strength J minus A, this will have interactions in J plus A. So Jij can be non-symmetric. So supposing we put this whole thing on a lattice. Okay, so Abhishek, you are again worried. So we can take time. What's the worry? You sure? So it's literally, I mean, the idea is really this vision cone thing, that if you can see better in front of you than behind you or something, you know. Or it could really be based on some signaling protocol which is very direction dependent. The point really is that interactions based on signaling are not reciprocal. Something is traveling, even if you're not traveling. And yeah, so there's an interesting technical issue which I'll take a few seconds on. We're putting this on a lattice. And we're introducing our original mental picture was of planar rotors, rotation invariant. We want an XY model to develop long-range order. We don't want to introduce lattice anisotropy and trivially turn this into a 4-state or some number of state clock model, right? Because then that would have long-range order for boring reasons, right? So the question is, now that I started to contract my order parameter with lattice directions, am I doing something? Am I trivially making the model order? Well, let's just check that. Let's actually work out this interaction. So let's do a little bit of algebra. Okay? The torque on the ith rotor is pi cross jij pj. Jij is j plus, sorry, by the way, I'm assuming, given that other people have been doing algebra, that it's okay to do algebra in a talk. Jij is j plus blah pi dot rij. And the rij's are these 4 vectors, or 6, whatever you want. In this case, these 4 vectors. Right? So I'll do the usual sort of informal gradient expansion. I'll say that P at J is P at Ri plus one of these vectors, which is P at Ri plus lattice vector dot grad Pi dot dot dot. So I'll write this in a gradient expansion. I'll thereby write the direction dependent part of the interaction, A Pi dot Rij times Pi dot Pj, using this expansion. Yeah.
The GIJ depends on PI itself.
Yes.
I mean, would that not break automatically time reversal invariantly before?
Well, of course it will finally.
No, but I mean, where is I was hoping to see that GIJ is just not symmetric, but no longer depending on the PI.
Well, you could do that, but I want one that does depend on PI, because my PI is which way I'm pointing and which way my eyes are directed. So I want to specifically put in a vision cone based. You could do other kinds of non-reciprocal interactions. I'm doing this one.
Yeah, because now it's like the third pole in the P, right?
Yeah, so it's not because of that I mean, you could break P going to minus P symmetry by some other means. That's not time reversal exactly. You could even imagine writing down some oddball energy function in which there was an external field defined, right? I could just put on an aligning field. So that doesn't break time reversal invariance. So finally, what I'll find is a term that can't emerge from the variational derivative of an energy function coming into the model. That doesn't require just breaking P rotation invariance. I could do that. I could introduce a preferred vectorial direction by putting in an external field, for instance. Not the same thing.
It's different from like Gij, Si dot Sj.
Right.
Is given. Here it's not.
Yeah.
It does depend on the.
Yes. Yeah. But the fun thing that happens when you do this, and you sum this guy over the 4 neighbors, is you will get this. And this sum for the 4 lattice vectors is the identity. And so you get a torque which depends on P dot grad P. You can expand this up to diffusion order, up to Laplacian order rather, and you still don't spoil rotation invariance. So even though I start out by making a rule that is based on lattice directions, up to Laplacian order, I'm fully isotropic. I'm therefore entitled to use this model to study ordering in planar rotation invariant spin model.
To Laplacian.
Yeah, that's good enough for me.
It's like, in magnetic interactions also, if you have cubic symmetry,
Right.
you just get the same as a sphere. But 4th order, you actually.
Well, I mean, it's true absolutely that given that this thing is on a lattice, I could always worry about what about terms that boringly. So, of course, I mean, but that's true for Heisenberg model on a cubic lattice also.
Sure.
Right. So I'm staying away from those. I'm not spoiling the game by the particular terms that I'm introducing. That's all I'm saying. Absolutely, any of the usual considerations that would render various spin lattice couplings system, yeah, can't escape any of those. But the main point I wanted to make is you don't need the physics of Jose, Kadanoff, Kirkpatrick, and Nelson to save you from these anisotropies. And so the continuum theory looks like this, okay? And this is actually in the limit where this, by the way, all the non-reciprocality is encoded in the coefficient A. The sort of purely uninteresting, ordinary interaction coupling is J. Models of this sort have been studied without non-reciprocality in various settings. Non-reciprocal Heisenberg or planar spin models have been studied by the Rome group in a slightly different context. The first and nice thing to see from this model is that if you say, look, you've got this damping on S, you can get rid, therefore you can say that on time scales large compared to chi over eta, I can relax S to a value determined by P, right? So I'll throw away ds over dt and solve for S in favor of this stuff. The effective equations of motion I get for P look like planar spins, but with self-advection, right? So what I get, therefore, is a fixed length version of a Toner 2 model, but without the density. So this is a model in which no spin is moving anywhere in space. I've got spins fixed on the lattice. I've taken the continuum limit of that model, and what I get is a model in which the orientation advects itself. The point is, this would never, it's not merely a breaking of P of some sort of ordinary invariance, because everything is nicely rotation invariant, and yet I have this term. You could imagine getting other kinds of terms with two P's and a grad in the equation, even from an energy function. If in the energy function you put in del dot P times P dot P, for instance. You don't even, you break P going to minus P invariance without breaking rotation invariance. But that wouldn't give you this term, that will give you gradient of P squared or P times diff P, neither of which turns out to be relevant for the transverse modes in the ordered phase. So they don't change the properties of the broken symmetry mode. Only this guy does, okay? And so this, if you like, this is what John Toner very annoyingly calls the Malthusian flocking model, because you take their original equations and introduce birth and death, and thereby make the density, knock the density out of the reckoning. And so this equation, the nice thing, I mean, the reason we liked this is you get this without actually any motion. So even though motility seemed to be important, flying spins seem to be important. Just flying information about the spins is all you seem to need. Okay, you get this model. And you can study this model. I mean, first of all, you can actually, it is reasonably well established by various arguments that are correct qualitatively, if not, though not quantitatively, that this model in 2 dimensions with a noise has a low noise phase with long range order. Okay? So the only point I wanted to make up to this stage, how much time do I have? 10 minutes? Huh? 15 minutes? Okay, yeah. The only point I wanted to make is that including questions. Yeah, right. Yeah. So non-reciprocity rather than motility is really the key. Okay. You can study now. I'll go back to the lattice model. So Pankaj Popley, who is the main person working on this currently, studied 2-point correlators in the. We went back to the lattice model. Pankaj, you know Pankaj. Yeah. Went back to the lattice model and studied 2-point correlations with and without the non-reciprocal interaction. And the 2-point correlations in the low noise regime indeed decay to a non-zero value at infinite distance, at large distance. You can also measure just the total magnitude of the order parameter as a function of system size, and it goes to a non-zero value. Yeah.
Looking at the lattice model,
yeah.
then you will at fourth order bring in the lattice anisotropies. Maybe they're irrelevant.
Yeah. They are certainly in terms of gradient expansion, they're irrelevant. Okay. Absolutely.
Maybe that's good.
Yeah. So yes. Yeah. So I don't. So we. Yeah. So, but that's a it's a valid thing to check that the only preferred directions we were able to find were ones that were imposed by the periodic boundary conditions box. That was a slight issue. Yes, but not the lattice. Yeah. So anyway, this model seems to show the PDE, the stochastic PDE has also been studied and has long range order. And the achievement here is, if you like, that the realization of a lattice model that does the same thing. Okay, but what is really interesting about this model is, so I mean, as far as we're concerned, this is the minimal 2D XY lattice model with long-range order. The rotors, each particle is the same as every other particle. Non-reciprocality is with respect to whether you're pointing towards or away from. So that's the idea. Sorry? Hmm?
When you see long-range order,
Yeah.
there's a direction, and that does pick up any.
No, it doesn't pick up lattice directions. Yeah.
If you're just looking for long-range order,
Yeah.
I guess there are other two-dimensional XY models which are non-equilibrium on the lattice.
There are probably others.
If
Yeah.
you add rotation in your
Yeah. So there are others. I mean, this is yes. Yeah.
I mean, that would not be related to the non-reciprocal interaction.
Right,
but
yeah.
Just for the long-range
Yeah, yeah.
order, there are others.
Sure. Anyway, what was I going to say? What's fun about this model is, not our model so much as even this PDE itself, is that it was recently shown by Bess, Chaté, and Solon that despite this behavior and the apparent existence of long-range order in these models, actually, if you run these things, if you wait around for a while, they blow up. Not numerically. There's an eruption of Astor defects. Okay? And actually, the question that we're most interested in is, can we understand why this happens? You can understand it in the sense of seeing that certain features develop when you study the numerical problem. What we decided to do was, if you take a look at this equation, you realize that there's this P dot grad P and this del squared P, and this is an awful lot like some, a kind of a flow in a direction set by P, advecting everything. And the question is, does that somehow prevent the defects from really seeing each other? So suppose you start out with a configuration with a +1 and a -1 topological defects. Is there tendency to annihilate in the low noise phase? Is that somehow inhibited by the presence of this interaction? So there's a length scale. Clearly, the ratio of A to J, J to A gives you a length scale. Does that length scale somehow do something? So that's the idea. And so actually, Pankaj studied this purely numerically. He took the lattice model and so I don't know how, let's see how well this works. So that's a +1 defect, that's a -1 defect. What you see is, okay, the way the model has been defined, the self-advection is proceeding in that direction. The distortions produced by this guy get swept into a kind of arc. But most importantly, these two guys sit and do not annihilate. Okay? So you can put them quite close to each other and they don't annihilate. So you can place them slightly off-center, and then they seek out this configuration where one hides behind the other. So let's start it again. So you can kind of see that, right? This guy is moving down, it sits there and just resolutely refuses to annihilate. By contrast, if you do this for an ordinary XY model, they quickly annihilate. Go away. Yeah. And you can look at how, basically you can ask for a given value of the non-reciprocal coupling, how far apart they should be before they fail to rebind. And roughly speaking, it looks like if you go to lower and lower non-reciprocality, you have to place them initially farther and farther apart for them not to see each other. Roughly speaking, that length seems to scale as 1 over the non-reciprocal coupling. So it does look like the non-reciprocal coupling introduces a length in the problem, which is roughly the length scale beyond which these guys somehow don't sense each other. Yeah. Various other fun things happen, if you include inertia, but I think maybe I won't talk about them. Let me go on to, let me summarize this part and then spend the next, 5-7 minutes on another story. So the major finding, if you like, is that the non-reciprocal interactions seem to cloak the interaction between defects, prevent them from seeing each other, and appears to be the reason why, if you have a system with that advective nonlinearity, eventually defect configurations arise from which the system doesn't escape and the system disrupts itself. I mean, so, yeah.
I'm not clear on what is the statement you're making.
The statement that we're making is that it was found that toner 2 PDE, if you like, with noise, even though a spin wave analysis showed that stiffnesses are enhanced and you should get long range order, the same model studied numerically eventually led to a defect proliferation of a type quite different from what you get in the high temperature or high noise regime. There's a nucleation phenomenon, and once those few asters nucleate, sort of all hell breaks loose. It looks like what we're offering as the reason for this is that the advective nonlinearity actually somehow conceals the defect strain fields from each other. And we did that in a purely empirical way by placing topological defects and seeing what they do. And the advection seems to prevent them from annihilating. That's essentially the finding. Okay, so let me switch gears, or at least switch numbers of components, and study a quite different model. This is a PhD work of Nisarg, jointly with Subrata Mukherjee in our department. And you all know the dynamics of ordinary classical Heisenberg spins, and you know that it conserves the total energy and the total magnetization. So let me skip all this. We got interested several years ago in what would happen if you had a left-right asymmetric interaction. So a spin here interacts differently with a spin on its right from a spin on its left. And what that means is that spin, you're the spin on its left. And so, again, it's a different kind of non-reciprocality with respect to an absolutely defined direction on the lattice. We got interested in this for reasons that no longer matter. It was a long time ago. But we started playing with this model again. So this was very old work with Jayjit Das and Madan Rao. What we had found back then was that the model sort of descended into a chaotic state, and that's about all. But we decided recently to revive this model and study the extreme non-reciprocal limit. And so you have a dynamics of this form. Sn dot is Sn cross Sn plus 1 minus Sn minus 1. This limit turns out to be simple because it turns out that though the magnetization is not conserved and there's no, the usual Heisenberg energy is not conserved. Where have I defined it? Yeah. If you define an object epsilon n of this form, S at a given site dotted with the difference between S at neighboring sites on either side, and the staggered magnetization, which we define this way, then it turns out the staggered magnetization and this weird pseudo-energy are conserved. So we wondered if perhaps there'd be a nice, smooth hydrodynamic description for these variables. Now, if you take this equation of motion and rewrite them in terms of the staggered magnetization and the direct magnetization, then you find that the staggered magnetization is a conserved guy and looks like this, and the pseudo-energy has a dynamics that looks like this, and the regular magnetization has a dynamics that looks like this. You can check that this doesn't conserve the magnetization. This manifestly does conserve n, and this conserves epsilon. This is, of course, the naive continuum limit, just taking these equations and replacing the coarse-grained versions of products of objects by the products of the coarse-grained objects. But if you study this model numerically, what you find, if you study two configurations which differ by a perturbation of a spin at one site, the decorrelation, the lack of overlap between those two configurations spreads in space ballistically in a manner very similar to what happens in the regular Heisenberg model, as was shown by our friends at ICTS a few years ago. There's a ballistic spreading of decorrelation, and a kind of statistical steady state emerges. Now, in that statistical steady state, presumably, the fact that the magnetization is not conserved will mean that the coarse-grained dynamics should acquire a relaxation time. Numerical studies reveal that the total magnetization does relax in a finite time. So you can write down a phenomenological equation like this for the direct magnetization, and thereby take the equation for the staggered magnetization and solve for m via this equation, and get an effective dynamical equation for the staggered magnetization, and similarly a dynamical equation for the pseudo-energy. And what you find is that that equation, in fact, if you assume the staggered magnetization is on average isotropic, in fact gives you a diffusivity. You can then study these behaviors numerically in the underlying lattice model, and what you find is that this is the steady state correlation function of the staggered magnetization. This is the steady state correlator of the energy. Both fit nicely to a diffusive collapse. So it looks like there's an emergent hydrodynamics in this funny model. What it's good for, we don't know. So what it suggests, though, is that this purely antisymmetric or purely non-reciprocally interacting model undergoes a kind of thermalization, and a kind of simplicity emerges in its long wavelength dynamics in terms of conserved variables, which I guess don't follow from any Hamiltonian. Okay. And with that, I'll stop, and that's my summary.
Thank you.
What happens if you add noise to the OT chain, to the Heisenberg chain?
Yeah, so I mean, to the regular Heisenberg chain or the weird one?
The last one, yeah, the last.
Yeah, I mean, I don't know, because it's already, it anyway is chaotic. It becomes noisy on its
Yeah.
own. So one could add noise to it.
Because
see
I'm
if
asking
they're
you,
not.
if you do that for the easing model,
Yes.
and you only look asymmetrically, it's a non-equilibrium system. You
Right.
do a global dynamics, but you get that the easing model is stationary.
Right.
So I'm just
No,
wondering.
is stationary meaning?
I mean, is invariant under the dynamics. It's not in equilibrium,
Yes.
but it is.
So this also settles down to a stationary state. Even without a noise, the system settles down to a statistically stationary state.
And which one?
It's one in which, n is conserved and this other pseudo energy is conserved. So steady states are presumably labeled by the total value of this oddball quantity, this scalar quantity, which is like an energy, and this vector quantity, which is like the total staggered magnetization. So even without noise, I'm saying that's what happens. And it is in that state that we do these calculations and try to estimate diffusivities and so forth. Yeah.
I was wondering, in the first example, once the ordered phase is destabilized, do you have in the end a finite correlation length due to the multiplication of defects, or is it quasi-long range order?
No, it's a finite correlation length.
Okay.
And that was already known in the studies by Bess et al.
Okay. Thanks.
Sorry, Shriram, maybe you mentioned so only in the extreme non-reciprocity, you have these conserved quantities, or
Yeah.
even if JL not equal to JR, you can write some generalized.
Couldn't find one.
I see. Okay.
Why the separation between the defects? What
No,
sets that
so
separation?
I don't know why they seem to stay a fixed distance apart.
And what controls that distance? Like, does the cone angle control it?
No, so the first ones, we placed them a certain distance apart, and they were far enough apart that they kind of were so screened from each other they didn't do anything else. Right? It's a little bit like if you had, supposing you had, I don't know, a diffusion cloud and you put an advection on it, so you moved that whole cloud away. Then if you put something else here that is going to be influenced by it, it would basically stay where you put it. As far as I know, it more or less stays where you put it.
I see. Okay, thanks.
If it's outside this magic distance. If it's close enough, they annihilate. How far they have to be before they don't annihilate depends on. By the way, those studies are with noise, just in case, meaning otherwise it's meaningless to. So it's with noise.
So, I mean, even though it's not exactly the Hamiltonian, but you have two conserved quantities. So, I mean, eventually it goes to some invariant measure which is given by these two conserved quantities. Is that right?
Yeah, so I think the honest answer is we don't understand terribly well what the steady state is, other than that it presumably is labeled by these two quantities.
Okay. And then, I mean, if you wrote like fluctuating hydrodynamics for this system, I mean, it's not obvious that it should be diffusive, right? Like you could.
It wasn't obvious. You can do the following actually. You can, if you take these equations, so let's say you phenomenologically write down this equation, phenomenologically similarly write down a conserved noise version of this guy.
No, but no, why for M? You write for N, but let's say N and energy, right? Because those are the conserved fields.
Yeah, sure. And you don't need M, indeed. Yeah. So
Right,
N energy, you can write, so what you'll do basically is, you'll write down this equation plus diffusion, this
Right, yeah.
equation plus diffusion, and plus a conserving noise in each case. And then you can ask whether the nonlinearities, see, one way of viewing this is that you can think of this as a kind of bare picture, and now you can divide the modes into short wavelength and long wavelength, and try to get an effective theory for the long wavelength modes in terms of short guys. We haven't done that formal projection. If you do that, you can also ask whether the nonlinearities change the scaling behavior from what this theory gives. They don't. The nonlinearities turn out to be irrelevant. So, I mean, that's kind of the full story is that as far as we can tell, the bare theory allows diffusion. We can find a quick and dirty argument for why you will get diffusion by eliminating M in favor of N. And then you can ask if the nonlinearities change it, and they don't change it. That's essentially it. I mean, you can write down diagrams and count powers and such like that. Somewhat disappointingly, the scaling remains diffusive. The spreading, there are the kind of weird features that people saw in the spread of the arrival time in Heisenberg. Similar things seem to be seen here, and we don't understand here either why they're seen. You know, there was this 1/3 law in the spread in Heisenberg, in Avijit Das and company's work. There are similar things seen here, but we understand even less here because we understand this model even less.
No other questions, and let's thank.
Thanks.
Next we have Prashant Singh.
I don't remember where my stuff is. Oh, excuse me.
Yeah, so my name is Prashant, and I'm a postdoc in Niels Bohr Institute. And my talk is going to be about stochastic thermodynamics, and I'll particularly talk about way to infer entropy production for time-dependent systems using some quantities which could be measured experimentally and which doesn't require much details about the system. And this talk, this is a work done in collaboration with Karel Prosmans from Niels Bohr Institute, and this is the reference for the preprint. So I'll begin by recalling some basic ideas for stochastic thermodynamics. So standard thermodynamics is a branch of physics that deals with macroscopic systems. And it tells us about the rules that govern the conversion of one form of the energy to the other in these systems. We have the first law, which is the statement about the conservation of energy. And the second law, which tells us that in any process, the total entropy change is a non-negative function. So over the last 2 decades, there has been development of a framework which allows us to study thermodynamics of stochastic systems, systems where thermal fluctuations become important and which can be arbitrarily far from the equilibrium. And to illustrate the idea, let us think of the dynamics of a Brownian particle in the overdamped limit. And this is the equation here, and U is the time-dependent potential, the conservative part, and F is any non-conservative force which might be acting on the system. And given this equation, we can get different number of trajectories. And what stochastic thermodynamics does is it gives us a way to associate these thermodynamic quantities for single individual trajectory. For instance, heat associated with a trajectory is defined in this way. This is the force acting on the particle from the bath times the displacement integrated over the time. And this is the work which has the time derivative part from the potential and the contribution from the non-conservative force. And once these definitions are taken, then we can show that there's this first law, but at the level of one single trajectory. Similarly, one can define entropy production, and when we talk about entropy production, we have to talk about systems entropy and the environmental entropy. So environmental entropy, throughout this talk, I'm going to make the assumption that the bath is at equilibrium, and it's defined by this temperature T. And once this assumption is made, the environmental entropy can be related to the heat in this way. And the system entropy is given in terms of the probability distribution here. Once again, the x that appears here is a stochastic quantity, which means that this is also a stochastic quantity. And the total entropy produced for that trajectory is given by the sum of the system's entropy and the environmental entropy in this way, which once again is a stochastic quantity. We can ask what is the mean of this quantity, and for the overdamped case, one can show that it's given in terms of this V function here, where V is related to the total force acting on the particle and the probability distribution itself. This shows that the average entropy production is always positive, and it's 0 when for the equilibrium case when the distribution is represented by Boltzmann distribution. Moreover, if an experimentalist wants to use this formula to, say, experimentally infer entropy, then it's a kind of difficult thing for two reasons. First, you need to know like what the precise force acting on the system is, and if there are multiple particles involved, one also has to know like what the precise nature of interaction between these particles are, which experimentally is kind of difficult. And secondly, this probability distribution is also here, and one often requires a large number of trajectories to get this distribution. So this formula, although like it's important, but to implement it experimentally is kind of difficult. And in the last few years, people have come up with some indirect ways to infer entropy production for systems. These are the two works, like one is by Srikant, Deepak, and Supriya, and this is based on thermodynamic uncertainty relation. And the other one is by the group of Edgar Roldan, where they looked at the discrete case, and instead of looking at the individual transitions, they focused on the coarse-grained picture, and based on the waiting time distribution in this coarse-grained states, they could get an estimate about the entropy. And both of these works dealt with steady-state systems. Plus, there are some other works for these systems. But in my talk, I'm going to focus on time-dependent systems, and I'm going to present. I am going to look at the time-dependent systems and try to make an inference about the entropy production for these systems. And I should emphasize that there are some other works in this direction recently, like Supriya has, Supriya and her collaborators in this paper, and Lee and others have also done some bit in this direction, but I'm not going to talk about the work and just focus on mine. All right, so let me now come to the method. So our method gives a general bound on the entropy production in terms of the moments of x of the position. For example, if in terms of the first two moments, in terms of the variance and the mean, we could show that the entropy production is bounded in this way. And everything on this right-hand side is expressed in terms of the first two moments, which means if I now could have some number of trajectories, I can use those trajectories to calculate these moments, and just from these moments, I could make an inference about the entropy production without having required like much details about what sort of force is acting on the system and those sort of things. Okay, so let me now very briefly walk you through like how we get this bound. Okay, so this is the entropy production, and I want to get a bound on this when I know, let's say, the first moment and the second moment. So these are the constraints that I have there, and I want to, so what I do is I include the effect of these two constraints via this Lagrange multipliers here, and I consider the optimization of this overall action functional here. And if you put the explicit expressions of this total entropy production and moments and all that, then you get this form here, where V, recall, is given in terms of the force here and in terms of the distribution. And interestingly, this V also turns out to appear in the Fokker-Planck equation, and this turns out to be crucial for the calculations. We now want to optimize this actional with respect to force, with respect to the force, because that's something we don't know. However, it's kind of difficult here because first this V itself depends on force, but the distribution that appears here, that also depends on this force via this equation here. So, and for any generic force, we don't know like how it depends on how the distribution depends on it. So that's why like it's sort of difficult to do this optimization. Maybe numerically one can do, I don't know. But we take this actional, and what we do is we introduce an auxiliary variable, this y, which is related to the v function in this way. And by using the certain properties of this y variable, one can rewrite this entire thing just in terms of this y variable here. And when we do that, we get rid of the final distribution here, and rather the initial distribution comes here. And moreover, like the force dependence can be incorporated just in this y functional here. But this is now like easy to control because we don't have the final distribution here. So we can now think of this as an actional in terms as an action functional in terms of this y and its derivatives. So what we do now is we do the usual thing in that we do in mechanics. We do the optimization, and when we do that, we get the Euler-Lagrangian equation of this sort with two boundary conditions which are given here. And all of these functions like mu's and zetas that appear here are known. So what I have done is by introducing this y variable, I have taken the problem of optimizing an entropy in terms of a problem in mechanics. And now we can solve this problem explicitly. And using this this y solution, we can get a bound on this total entropy production, and this is what we obtain. And once again, I would like to emphasize that everything on the right-hand side is given in terms of the first two moments, which means we could use these trajectories and compute these moments and see like and get an estimate about the entropy production. All right, so once we have this, now I want to ask like how strong this bound is, how tight this bound is, and we tried applying this to an experimental system of bit erasure, and yes, this is the average entropy production. Okay, so I'll apply this bound in the context of an experiment on bit erasure. So just one slide on bit erasure. Like Landar in this paper argued that in order to carry out the erasure of a bit, there is some minimum energy that one has to give. And for the simple case of when one has just two bits, like say 0 and 1, and if you do some erasure operation such that it gives you just one output, then he showed that the work is bounded in this way by kBt log 2, where the equality holds only in the quasi-static limit, where you carry out this erasure operation very, very slowly. In that limit, the bound is this equality holds. Now, this is important for two reasons, because first, it tells like information is physical, and it links information with the thermodynamics, and that's fundamentally important. And second, from the application perspective, it also gives us an idea about like what are the energy costs associated with computations. Within stochastic thermodynamics, recently people have tried to verify this bound using some experiments, and this is just the sketch of an experiment. So initially, so there's a double well potential like this, and initially the particle could be on this side or on this side. So if it is on this side, this is like state 0, and if it is on this side, then this is like state 1. And over the course of time, you manipulate the shape of this potential in such a way that the particle always ends up on this one direction. Which for our case is this state 1. So this is the sort of erasure operation that I was telling you before, and so this is the precise potential that they considered in the experiments, and this is the final time, like the cycle time t final. If you look at trajectory, at the level of trajectory, it would look something like this. Suppose if you start on the left side, you would end up on the right side. And if you start with from the right side, you would eventually stay there on the right side only. So for now associated with each of these trajectories, one can define, one has the work in this way, and we have the form of potential here, and experimentally now, they looked at this average work, and experimentally they saw that, I would want you to look at this blue curve. Experimentally, they could see that as you go to higher and higher cycle times, the work more converges to this bound log 2 here. So we took the experimental trajectories, and I should emphasize that this work was done by a group of John Bakehofer, but there was a similar experiment before by Siliberto's group. So we took these trajectories and we, looked at this. We have this bound here, so we calculate these first 2 moments using these trajectories, and even with very less than 100 trajectories, we made the inference, and this is the plot here. So this green curve is the simulation result, because you know the exact form of the potential, so you could simulate it and obtain this form. And this red symbols that you see here is the inference made using this formula for different values of the cycle times. And we see even with of the order of 50 trajectories we have considered, and even with that, we could see it's very close to the actual value. This is also another example, but this is more theoretical because this is simple and we could do things analytically. And here, this red line is the analytic exact line, and these green symbols that you see here are is the inference made with the first 2 moments. But now one can go a step ahead and say, suppose instead of first 2 moments, I have the first 4 moments, say, then I'll do better. And when I do that, these blue stars here are the results that we get. So this is the summary. So we have derived a general bound on the mean total entropy production for time-dependent systems in terms of quantities which could be measured experimentally, and which for our case turns out to be moments in the correlation functions. We then applied this bound to the experimental system of beat erasure, and we found that the inferred entropy production is very close to what we get from the simulation. And even though in my talk I focused on just the first 2 moments, one can extend it to general moments, arbitrary number of moments, and even to higher dimensions. And this is the reference of my paper, and I would like to acknowledge John Bakehofer and his student Prithviraj Bosak for helping us with understanding the data. Thank you.
Yes, open for questions.
So Prashant, how does your bound that you got compares with the bound that you get from the TUR? So the quantity that you're looking at the right side, they are also time-integrated quantities.
Yeah, but TUR, I think it holds only for this steady-state systems, and only when you, I think Supriya and they showed but if you look at the system at very small time limits, then even for time-dependent systems, the bound seems to work. But here we did not make that comparison.
So
we
if
just
you look at the term there, and if you try to express everything in terms of x dot, they would not relate to any time integrated quantity.
But they don't have derivative, right? Time derivative in TUR. Yeah.
This is some current variance, so variance and mean of current, and so
but they
the
don't
expression that you look at there, so integral of x dot is the current for this problem. The Langevin problem. So is there any relation of the right-hand side with the current?
Yeah, but I don't know, because I thought about this, and this one seems to involve the time derivatives, but there we don't have that. Yeah.
All right.
Yeah.
Thanks.
Yeah.
So your relation, will it reduce to TUR if you consider a steady state?
Actually, no. For steady state, this just becomes the trivial bound, because all these derivatives go to 0, and that's because we have considered just one-time property in our description. Here I look at this one-time property. So if you want to make a comparison with TUR, you should really consider x0 and xt, and whether you could reduce that problem to this problem is not clear. If you have, this is one-time property. With two-time properties, I don't know whether you can do this reduction.
Okay, so I have another question that if you consider third and higher movements, can you make your bound more tight? Or?
Yeah, so that's what I think I showed here. Here this green is with with just first 2 moments, and the blue one is with first 4 moments, and you see like it's, I mean, this is matching, this is more closer to the exact one for the one with first 4 moments.
Yeah, okay. Can you show that this series is monotonic? Like you keep adding the moments and all of them get, or is there some oscillatory convergence?
Here.
Yeah, in the bound.
Yeah, where was it?
And then as you add higher and higher moments, you always get a better bound, or could there
Here.
be oscillatory? And
Oh, this bound.
yeah,
No, it becomes better. I don't know whether it becomes oscillatory or not. It goes more towards the exact value.
I see. Okay, thanks.
Is it possible to also get a upper bound, or like from some, is there some other work which also gives you upper bound to the entropy production?
You have, I don't know.
No more questions?
Yeah.
Thank you.
Yeah.
Yeah. I just want to quickly remind you that basically there's a museum visit today and tomorrow. So whichever day you prefer. So if you want to go now, basically you can just walk out, and then it's just the end of the corridor, basically. Yeah. So they can accommodate up to, I think, 25, 30 people. So yeah. So maybe like how many people want to go? Yeah, today. So you can just start walking maybe, or you can have a tea and then start walking. Yeah.